Most people think that a histogram is a bar chart but without any gaps. That's not a histogram, right? Please remember a bar chart can have gaps or it cannot. It doesn't make any difference. They're both still bar charts. Bar charts are usually used for discrete data like number of pets. You can have 3 pets or 4 pets or 5 pets, but you can't have 5.73 pets, we hope, right? Histograms are graphs in which you are looking at frequency density instead of frequency. So very importantly, on this axis, we've got frequency density, and then we have our variable over here as usual. So if you don't label the y-axis as frequency density, you're going to lose a mark there. They don't take that well at all. So say, for example, in fact, let me look and see if there's a good little table inside the textbook. Just pause that. Okay, so if you look at this table over here, this is typical histogram data. It's got its class intervals, so we've got from 0 to 20, 20 to 40, 40 to 50, 50 to 70. So very often you either have continuous data or you have class interval data. So obviously, if I was going to make a graph of your results for the exam, it would make more sense to make a histogram than to do a bar graph. If I did a bar graph where each person in the class is a separate bar, you'd end up with a fairly meaningless graph, right? Whereas if I group you together and I work out how many people there are in the 60s, how many people there are in the 70s, how many people there are in the 80s, that is a much more meaningful way of understanding what the results actually look like. So class interval data is very, very common, and the other one is continuous data. So for example, if we look at height, your height, you don't know exactly what height you are. So you might think that you're 182 centimeters, but you're actually not. You're 182.3 or 0.4 or 0.5 or 0.5793581. It's for continuous data where we can have any value. It is possible for every single human being in the world to be a completely different height from every other human being, right? Because it's continuous data, and if we're going to look to 20, 30, 40, 50 decimal places, we can have somebody who has those differences, right? So these things are suited to this sort of data, which is most of the data, right? So histograms are used very commonly. There's another difference there. Can you see something about those class intervals that is different from the most of the graphs that you usually see? So, okay, one thing to notice that Kate just pointed out is that we have got class boundaries here. So because we're using inequalities, we know exactly where this ends. Doesn't go up to 20, goes up to 19.9999. This one starts exactly at 20 and goes up to 39.999. So those are called class boundaries. A class boundary is when they tell you exactly where the class starts and ends, and that's a blessing. When you're in year 12, they'll give you class intervals, which are rough guesses. In other words, instead of saying 0 to, it'll be like this. It'll be 0 to 20, and then 21 to 30. Then where is 20.4? Which group is it in, right? And you will have to work with class intervals and convert them to class boundaries. So that is the step up for year 12. It's a very small step. It's not very difficult. But you don't need to worry about it in year 11. They tell you exactly where it starts and where it finishes, which is a blessing. And if for some reason they don't, they still don't expect you to worry about it. So I'm actually not going to discuss it much now. But those are class boundaries. You know exactly where it starts and ends. That's what we want, right? In addition, what can you say about the width of those classes? Are they all the same? If you look at the first one, it's 20 units wide. Do you agree? Are they all 20? That's what makes it a histogram, right? So as soon as we have class intervals that are not the same, so if you look at this one, and this is the thing they expect you to fill in. They don't expect you to do it in your head somewhere. They expect you to write it down and show the working, okay? So you look at the first one, the class width is 20. There are 20 marks in there. Second one, class width is also what, 20, yes? Third one, class width is? Fourth one, class width? And last one. Okay. So if you were to plot these things and you were to do them incorrectly, and you started here and you said 0 to 20, and I'm going to put my first bar there, and then I've got 20 to 40, obviously you have to use correct scaling. So if 20 units must be 20 units throughout. So obviously if I go 40 to 50, that's going to be narrower, right? And then 50 to 70 is there. and 70 to 100 is saved there, right? If you went and put them in at the frequencies that they're currently at, so this is wrong what I'm doing. So let's say that this is 10 here. I'm just looking to see how high are the frequencies, 36. So this is 10 here, this is 20, this is 30, this is 40. If I went and put them in more or less, first one is 28, so it's going to be there-ish. By the way, they're very fussy about you getting this right. So if you go and put it at 27 when it's 28, you're going to lose the mark, so can you not do that? This one is 20 there. Then we've got 30 for 50 to 70, which is there, sorry, there-ish somewhere. And lastly, we've got 18 for 70 to 100. Can you see why what I've just done is rubbish? So I've plotted frequency. Notice that on my y-axis it says frequency density, clearly not the same thing, but I've plotted actual frequency instead. What is wrong with the graph? It's distorted, but why? What is it suggesting that is not true? Look at the last category. There are 18 people between 70 and 100. Is that a lot of people? Or are they spread out quite finely? Do you agree that that's 6 people between 70 and 80 more or less, and 6 between 80 and 90, and 6 between 90 and 100, right? So it's very low. Do you agree? Does it look very low? It looks like it's comparable to the others. And this is because when you plot something as a big block, the area of the block makes a visual impact, right? And so because you've got a big area there, it looks like there's a lot of people there, and there aren't. In actual fact, we've got 6 people in each category. And surely if you read this off, if I didn't give you the table, and I asked you how many people were between 70 and 80, and how many between 80 and 90, surely you would read this off, and you'd say, well, there are 18 between 70 and 80, right? And there are 18 between 80 and 90, and there are 18 between 90 and 100, right? Which is complete rubbish. Okay. So you have completely distorted the data. It makes it look like there's a huge number of people in that top category, where in actual fact there's very few people. There's only 18 people in that top category, right? So we have to change it so that it looks the way it actually is. So the way histograms work is you are plotting frequency density against the variable, and frequency density is taking area into account. So it's frequency density versus variable, not frequency, right? And frequency density is equal to the class width divided by the frequency. Now, this is not a formula they're going to give you, but it's very logical. So if you're going to look at the very first one there, again, you need another column. So you need to actually put the column in. People try and, again, do this without any columns, without any evidence of what they're doing. And then if you get something slightly wrong on your graph, everything is wrong because you've got no workings and your answer is wrong. Okay? So you actually add it into your graph. Usually one would add the columns on the right-hand side, not the left-hand side. But it doesn't matter as long as they're labeled, just add in the columns. So we expect to see class width. And then you're going to say, take your class width, which in this case is 20, and you are going to divide it by, actually I'm giving the formula the wrong way around, I'm sorry, let me just switch it around. It's frequency divided by class width, not the other way around, sorry. So you're going to take your frequency, which is 28, and divide it by the class width, and get a frequency of 1.4. That is now your frequency density. For this one, it's going to be 1.4. So now we can compare all of them with each other. So the next one, we're going to go 36 divided by, so again, frequency divided by class width, which is 20, and that one is going to be 1.8. And then the next one, we're going to go frequency, which is 20, divided by class width, which is 10, and that one is going to be 2. And then we're going to go frequency, which is 30, divided by class width, which is 20, and that one is going to be 1.5. And the last one, we're going to go frequency, which is 18, divided by class width, which is 30, and that one is 0.6. And now you have them relative to each other, right? Now you can see where most of the people are. So most of the people are in the second class, the 20 to 40s, because that's good. If you think about it, that's 18 people per bar, whereas the first one is 14 people per bar, and the 40 to 50 is 20 people in a bar. So, that's, in fact, that's the highest. Yeah. So basically, you are going to be able to now compare them properly. And then on your graph, you are literally going to put frequency density. So let me do this in a pretty manner. I'll use the textbook one. So here they have done it nicely in the textbook. So they have worked out the class width, which they have not written down, which they should have. And they have said frequency divided by class width, and they've got the frequency densities. And then look at the histogram. That's a histogram. Always frequency density, not frequency. Okay? So if you want to work out how many people are actually in the bar, you have to go backwards. So they could give you a graph like this, and you can see that over here, the frequency density is 1.4, right? So they could give you this bar, and you can see, okay, frequency density is 1.4. This is going to be 1.2. Here's 1.4, 1.6, 1.8, etc., right? And you'd say, okay, the frequency density is 1.4. And they'd give you, say, and the class width, we can see it. There it is. It's 20. So class width is equal to 20. And if I want to find frequency density is frequency over class width. So I've got my frequency density, which is 1.4. I want my frequency. My class width is 20. And so x is equal to 20 times 1.4. Not exactly difficult stuff. And your frequency is actually 28. Do you see that? So here's an example of a nasty sort of question they can ask you. So this is about the worst question they can ask you for this, and they do ask it probably 1 in every 3 papers, so you must be able to do it, and we'll practice it. But basically, they give you obvious histogram data. You can see your class intervals are completely different. They give you frequencies, and then they give you one frequency density or something, and you're supposed to work out the rest. Now, the first thing to do for that immediately would be to work out the class widths. So immediately you'd put the class widths inside there, and this first class width is 10, this next one is 20, this next one is 40, and the last one is 5, right? So and then you would work out frequency density for the one that they've given you. So you would say, okay, my frequency is 17, my class width is 10, and my frequency density is supposed to be 1.7, right? But it's not, okay? So basically, what have they done to get from 1.7 to 0.85? So you're going to have to look at the relationship between the frequency density they've given you and the frequency density which is correct that you've just calculated. They're allowed to give you proportionate frequency densities. It doesn't have to be used in the formula, which is what they've done. Okay? What is the relationship between 1.7 and 0.85? Serious, is not hard.
One is 0.15.
Yes, we could add, but that's not going to work very well. This is scale factor. This is ratio. Our numeracy is not what it should be. That one is twice the other one. Okay, you're going to look at scale factor. They're going to do it by scale factor, which is multiplication, not addition. Okay, so you're going to look at this and say, how would I get from 1.7 to 8.5? Okay, and that's a ratio of times 2. Okay.
That's times 2?
Yes, 1.7 is the actual frequency density, and 0.85 is half of 1.7. Seriously, you're frightening me a little bit there. So you're going to basically work out the ratio, okay? So basically what they've done is they've taken the frequency density and they've divided it by 2 to get the 0.85. Do you agree? Okay? So you work out the other frequency densities and you divide them by 2. Seriously. It's a scale factor, it's ratio. They're just shoving ratio in your statistics, you lucky things, right? So in other words, you go and you work out for A, and A is going to be your frequency, which is 28, over your class width, which is going to be 20. So that is going to be 1.4. But we don't use 1.4 because they didn't just, they scaled it, right? They divided it by 2, so you divide it by 2. So this one is 0.7. Okay. And then the next one, again, you work out the frequency density, which is going to be your frequency over your class width, which is obviously 5/4, and you divide it by 2, which is 5/8, right? And then the last one, your frequency density is going to be your frequency, which is 8, over your class width, which is 5, and you're going to divide it by 2, which hopefully you know is 0.8, right? And if you don't, your calculator definitely does. The point here is that you have a ratio that they've used. So they're allowed to take the frequency density, and they're allowed to change it according to a fixed ratio. It'll be times 3 for every single one of them, or it will be times 3/5. Yes, they like that sort of thing. Or it will be times 1/2, or it will be times 0.6 throughout. You just have to work out what the actual frequency density should be and work out what they've done to that in order to get there. And so you can say, you can always set it up as a little algebraic equation. You can say actual frequency density times by x is equal to what they've given you, and solve for x, right? So you don't have to think, and then you'll know, then you just do the same for all the others. Okay, I'm going to stop that.